Hi, welcome back to Music Chemistry. This is Colligative Properties lesson number 4. Calculate the freezing point of a solution of 5.00 grams of C12H10 and 7.50 grams of C10H8 dissolved in 200 grams of benzene. The first thing I want to do is take the 200 grams of benzene and change it to kilograms of benzene. All right, so let's go ahead and do that because remember we're looking for molality. So we got 200.0 grams, and we want to change that into kilograms. And this is actually really easy. So you just take the 200 here, 0.0, and you move this decimal 3 places over, just like that. And that gives you 0.2000. So that was simple. All right. Now, what we need to do is we need to know a couple of things. We need to know the molar mass of C12H10 and the molar mass of C10 and H8. So let's go ahead and figure that out. So if we had C12, so we had 12 carbons times 12.01, and that number comes from the periodic table, of course, and we had 10 H's times 1.01, and that's also from the periodic table. The molar mass of C12H10 is going to be as follows. Give me 1 second here while I calculate this out. All right, this will give me 154.23 grams per mole. So it'd be 154.23 grams per mole of that one. So let's look at the C10H8. So C10 again is 12.01 and H8. So H8, and that's going to be times 1.01, and that's going to give me a grand total of 128.18 grams per mole of C10H8. Now we're ready to do this. Now look at this. We have two things. We have this and this. And they're put into a solution, so logic would dictate that we would add this together. So what we're going to do is we're going to go like this. We're going to go 5.00 grams of C12H10 times 1 mole of C12H10 divided by its molar mass, which is 154.23, right, grams of C12H10 plus 7.50 grams of C10H8, see that, times 1 mole of C10H8 divided by its molar mass, which is 128.18 grams. So when you do this, you find that this first one is going to be 0.032 plus 0.058. So that number came from there, and this number came from there. All right, so when we add this together, this is going to give us a total moles of 0.0905. All right, so now we're going to take that number and find the molality. So it goes 0.0905 divided by 0.2000, and our M value is going to be 0.453. All right, we're not quite done yet though, okay? Not quite. Okay, so now what we're going to do is we're going to now have to find the freezing point. We have the molality, and now we need to calculate the freezing point. So to do that, we need another formula. We need delta TF equals I KFM. All right, so benzene is not an ionic compound. So the Van Hoff factor, that I, this guy right here, is going to be 1, right? So you go delta TF equals 1 times, now benzene's freezing point, which is different from water, is going to be 5.12 degrees C over M. Where do I get that number? Well, unless you memorize it, you have to really look it up, okay? Times the molar, which is going to be 0.453 little m. We should have put a little m there. So m's cancel m's, and that gives me a grand total of delta TF is going to equal 2.32 degrees C. Now, what we're going to do is we had our original freezing point of benzene. The freezing point of benzene, of course, I should have wrote this down, but I didn't. The freezing point of benzene is 5.5. So if you want to know what the new freezing point of benzene is, you would go delta TF equals 5.5 degrees C minus 2.32 degrees C. So this is going to give me a new freezing point of 3.17 degrees C. So the freezing point of benzene originally is 5.5. So when you add this stuff together, the C12H10 and the C10H8 together, it's going to take and depress the freezing point of benzene from 5.5 to 3.17 degrees C. And that's it for this particular problem. That was a lot of work. Now, let's look at the next problem. Given 3.20 grams of C6H12O6 and 1 kilogram of water, what is the molality? All right, well, first of all, we need to know what the molar mass of C6H12O6. It's glucose. So it's going to be pretty easy. You get 12.01 here from the periodic table. And then, of course, your hydrogens, you got 12 of those, and that's 1.01. And then we have oxygen, we have 6 of those, which is 16.00. When we add all this up together, we get 180.18 grams per mole of C6H12O6. Right, now that we have that, we have to convert 3.02 grams to moles, right? So we go 3.20 grams of C6H12O6 times 1 mole of C6H12O6 divided by the molar mass that we just calculated, which is 180.18 grams of C6H12O6. So that cancels out, and that tells me that the moles are going to equal, let's see here, 0.018 moles of C6H12O6. All right, now we can figure out the molality. So we take our moles and we put them on top, 0.018 divided by 1.0 kilograms, right? So the molality is going to equal 0.018 little m. Now all we have to do is put it in the delta TB problem and we'll have our answer. So we go delta TB equals I KB little m. That I, that Van Hoff factor, is going to be 1 because this stuff right here, it's not ionic, so it's not breaking down into ions. So it's going to be simply, Van Hoff factor is going to be 1. So you go delta TB equals 1 times the boiling point of water, which is 0.51 degrees C over M, times our M value, which is 0.018 m, our m's cancel out, and our delta TB is going to equal, let's see here, let me get my calculator, double check this answer. Give me one moment, please. A second here, guys. And that's going to give me, let's see here, 0.51 times 0.018. That's what I thought it was going to be. It's going to be 0.00918 degrees C. And that's our boiling point elevation. So not only did we calculate the molality, but we also went ahead and calculated its boiling point elevation change. Well, that's it for this lesson, guys. You be snarly, and we'll see you back here at Moosine Chemistry.